Human beings were always intrigued by the question, what is this universe made of? The universe as we perceive it is either in the form of energy or matter, and they are all composed of subatomic particles. 100 years ago, we were aware of only 3 subatomic particles: protons, electrons, and photons. But today, we know more than hundreds of subatomic particles, and there's a special branch of physics which is completely dedicated to deal with their identification, classification, properties, and interactions. So welcome to a lecture on elementary particle physics. So first, let's see one basic classification of particles. They are bosons and fermions. Bosons are particles which does not obey Pauli's exclusion principle and they have integral spins, whereas fermions, they are subatomic particles which obey Pauli's exclusion principle and they have half integral spin. Now, what is Pauli's exclusion principle? We might remember from our earlier classes that it is a law which prohibits the existence of 2 particles simultaneously in a single quantum state. So, bosons are those particles that do not obey this principle, whereas fermions, they have to obey Pauli's exclusion principle. A few examples for bosons, as we can see, are photons, gluons, mesons. Now, photons are quite familiar to us. Photons are the energy carriers in an electromagnetic interaction. So, photons, they are quantum of light energy. Similarly, gluons, they are the particles which take parts in strong interaction. So, they can be considered as the carriers of strong force. Similarly, mesons are carriers of weak force. So, all these bosons, they could be like broadly said as energy carrying particles, or we can say they are energy particles. Right. Whereas fermions, they are matter particles. Examples of fermions are protons, neutrons, and electrons, and they constitute the matter in our universe. So the spin of the bosons, they will be either 0, 1, 2, 3, any integral number, whereas for fermions, the possible spins are half, 3 by 2, 5 by 2, or minus half, etc. This is not it. We can further classify subatomic particles as leptons and hadrons. Now, this classification is based on the interaction of the particle with a strong reaction, a strong force, which is also known as nuclear force. So, leptons are those particles which does not respond to strong interaction. And the other classification is hadrons, which are particles which respond to a strong interaction. So, leptons, we are having electrons, muons, tau particles, and neutrinos, whereas hadrons are further classified into mesons and baryons. One important difference between leptons and hadrons are, leptons, they are elementary particles. Elementary particles in the sense they are not composed of any smaller particles. So, leptons are elementary, they cannot be divided into any constituent particles. Whereas hadrons, as the name suggests, hadron means strong. So, they participate in strong interaction and they are composite particles. Hadrons are composed of further smaller particles, and those smaller particles which composes a hadron, we call them quarks. Maybe we can deal with quarks in another lecture. So this is another classification of particles based on their response to strong interactions. Let's see more about leptons. As we have already seen, leptons, there are charged leptons which are electrons, muons and tau particles, and neutral leptons, which are electron neutrino, mu neutrino, and tau neutrino. So these 6 particles together comprises leptons. But that is not all. All these particles have their corresponding antiparticles. So let's see, for electrons, you have positron as its antiparticle. Now for muon, you have mu plus antiparticle. For tau, you have tau plus antiparticles. Similarly, for neutrinos, you have electron neutrino and the antiparticle is electron antineutrino. You have mu neutrino and mu antineutrino, tau neutrino and tau antineutrino. So these are some examples of weak interactions in which a lepton participates. So now we have seen all the leptons. We are having 6 particles and their corresponding antiparticles. Now one important particle among the leptons that we are focusing is neutrinos. Neutrinos, they are also called as ghost particles. Why? Because at any given time, at the present moment, millions of neutrinos are passing through our body. So neutrinos, they are a part of the cosmic radiation and they are infinitesimally massless. Their mass is so small that it could not be detected. They have no charge, they does not interact with strong forces, and they have weak interactions with gravitation and weak reactions. So it is extremely difficult to detect or measure the properties of neutrinos, hence they are called as ghost particles. So in leptons, we have 6 neutrinos, electron neutrino, mu neutrino, tau neutrino, and their corresponding antiparticles. So how do you distinguish between a neutrino and an antineutrino? For that, we have an additional property known as helicity. Helicity, it will give you an understanding about whether the particle is right-handed or left-handed. So let's see what is this right-handedness and left-handedness. So when you see my right hand, if I curl it like this, my thumb is pointed in this direction. Let's see, there is a particle whose spin is in this direction, the direction in which I have curled my fingers. And its motion is along this direction, that is the direction of my thumb. So such a particle, you can call it as right-handed particle. Now when I consider my left hand, if I curl my fingers in this direction, my thumb is in this direction. So when you draw such a particle, okay, my fingers are curled in this opposite direction and the particles move in this direction. So this kind of particles we call as left-handed particles. So this is the property known as helicity. And it is observed in the universe that all neutrinos are left-handed and all antineutrinos are right-handed. So this distinguishes a neutrino from an antineutrino. Now let us see about hadrons. Hadrons are further classified into baryons and mesons. Baryons again classified into nucleons, which consist of protons and neutrons, and hyperons, which are some sort of strange particles. Few examples are omega, sigma, psi, and lambda particles. So these are some examples for hyperons. Now all these baryons are fermions, which means they have to obey Pauli's exclusion principle and they have half integral spins. And all the baryons, they are composed of 3 quarks. Whereas mesons are bosons, which means they are energy carrying particles. And mesons, we are having 3 different types. They are pions, which are denoted by a pi. It could be pi plus, pi minus, or pi 0. Kaons or K mesons, which are denoted as K plus, K minus, and K0, and etons or eta particles. Now all these particles, they have their corresponding antiparticles. So for pi plus and pi minus, they are antiparticles of each other. And pi 0, the antiparticle is pi 0 bar. Similarly, K plus and K minus are particle-antiparticle duo. K0 it have an antiparticle K0 bar, and for eta 0 we have eta 0 bar as the antiparticle. Similarly for baryons also, we have proton and antiproton, neutron and antineutron. So we are having a large collection of subatomic particles. Now among these hadrons, there is a special class of or a group of particles which are known as strange particles. They are the kaons or the K-mesons and hyperons. So hyperons and kaons are together called as strange particles because they show some sort of strange behavior. These particles, they are formed as a result of strong interaction, but they decay through a weak interaction. So this is sort of a strange behavior. That is why these particles are called as strange particles. And whenever they are formed, they form in pairs. So this is an example for a strong interaction. As we can see in this interaction, strange particles are formed in pairs. But each of the strange particle decays through weak interactions. So such particles, we call them as strange particles, and they are kaons and hyperons. So now we have seen a lot of subatomic particles. Now in order to have some interaction between the subatomic particle, certain conservation laws are to be maintained. Now we are familiar with the basic conservation laws of energy, angular momentum, charge, etc. But when you come to the subatomic realm, we have to do some more conservation laws. They are the conservation of lepton quantum number, baryon quantum number and strangeness quantum number. So lepton quantum number, as the name specifies, it is exclusively for leptons, that are for electrons, muons and tau particles. So there are three quantum numbers: an electron lepton number, a muon lepton number and a tau lepton number. So this Le, electron lepton number, is obeyed by the electron family. We have electron, positron, electron neutrino and electron antineutrino. Similarly, muon lepton number, it is obeyed by the mu family, and tau lepton number is obeyed by the tau family. Now baryon quantum number. Baryon number, it is again dedicated to baryons. So all baryon particles have a baryon number of 1. Their antiparticles have a baryon number -1, and all non-baryon numbers, they have B is equal to 0. The third one is strangeness quantum number. All strange particles, they have the strangeness quantum number in this range, and all non-strange particles, S is equal to 0. So these are some specific conservation laws to be satisfied for a particle interaction to take place. So now let us see few particle interactions. Before that, we have a table of all particles with their corresponding lepton number, baryon number and strangeness quantum number. So we can see that we are having electron and electron neutrino, which are leptons. So they have electron lepton number equal to 1 and all other quantum numbers will be 0. The antiparticles of these are positron and electron antineutrino. They have a lepton number of -1 and all others will be 0. Similarly for other leptons. Now when we come to protons and neutrons, they are not leptons, so they have lepton quantum numbers 0 and baryon number will be equal to 1. Whereas for an antiproton and an antineutron, baryon number will be -1. Kaons, they are neither leptons nor baryons, they are mesons. So they have all these quantum numbers 0, but since they are strange particles, they possess a strangeness quantum number in the range +1, -1 and ±1 for K0 and its antiparticle. Then here comes the hyperons. All the hyperons are baryons, so they all possess a baryon quantum number and they have their strangeness quantum number also. So once we know about these quantum numbers, we can identify whether a particular particle interaction is permitted in the universe. Let's see a few examples. The first interaction, we can see that we are having a mu plus. which is getting converted into a positron, an electron neutrino, and a mu antineutrino. So when we consider the quantum number, we have the muon quantum number L mu. For this is a muon antiparticle, so it will be having -1. For positron, muon quantum number is 0. This is also muon lepton number is 0. And for the antiparticle, we have this is equal to -1. So muon lepton number is conserved. Now electron lepton number. For electron lepton number of muon is 0. For a positron, it is -1. For a neutrino, it is +1, 0. So again, electron lepton number also is conserved. So this reaction is permitted. Secondly, we can see a proton, a neutron forming a proton, neutron and an antiproton. So first itself, we can see charge. A proton is having a charge +1, neutron is 0, again 1, 0 and -1. So it is clear that this reaction is not permitted because charge is not conserved in this reaction. Thirdly, we are having a strong interaction because two strange particles are formed, so it has to be a strong interaction. So this is a pion, pi minus particle. So let's see first the baryon number because we are having baryons here. Pi is a meson, so its baryon number is 0. Proton, baryon number is 1. Lambda, again it is a baryon number 1. K0 is a chion, which is a meson, so baryon number is 0. Now we have to see strangeness S. For pion, it is 0. For proton also, it is 0. For lambda 0, if you remember from the last slide, it is equal to -1. And for K0, it was +1. So both baryon number conservation and strangeness conservation is achieved. This reaction is also permitted. Similarly, when we see this reaction, you are having tau particle. So tau lepton number, this is equal to 1. Electron, there is no tau lepton number. There is no tau lepton number. And here it is a neutrino. So we have tau lepton number 1. So tau lepton number is conserved. Electron lepton number is 0 for a tau particle. For an electron, it is 1. And for an electron neutrino also, it is equal to 1. So here the electron lepton number is not conserved, which means that this interaction is not permitted. Here we are having a proton. So again we will be having a baryon number. Proton's baryon number is 1. Neutron is again 1. And these both are zeros. Fine. You have the electron lepton number. For proton it is 0. Neutron it is 0. For electron it is -1. And for electron antineutrino it is -1. Which means that it is not conserved. So this reaction is also not permitted. Finally, we have chions and protons. So we'll be having a baryon number which is 0 for chions, 1 for proton. This is psi 0, which is a hyperon. Hyperons are baryons, so it is 1. And for chions, again baryon number is 0. So baryon number is conserved. Then you have strangeness quantum number, K minus. It's having a strangeness quantum number, -1. Proton, it is 0. You have psi 0. Psi 0 has a strangeness -2 plus K0 is +1. So it is -1 and -1 on both sides. This reaction is permitted. So this is a basics of elementary particle physics. So let's hope to see more about that in the coming lectures. Thank you.